Hey everyone, right now we're going to learn about systems of equations and how to solve them. So let's get started. First thing I want you to see is I've given you a system of equations. What it involves is two equations that, and in this case, have two variables. So x and y are two variables. When the number of equations and the number of variables match, you can usually figure out what the two variables should be. So yeah, you notice, like, for example, 6 and 1, they work for the first equation because they add up to 7, but they do not work for the second equation. So the key is, often we need to find the one pair that works, and sometimes I'll give it to you and you just need to check it. So the only pair of numbers that work here are when x is 3 and y is 4. And because 3 plus 4 is 7 and 3 minus 4 is -1. And there are three main ways we're going to show you how to solve this. I want you to learn all three ways so you can use whichever one is easiest at the current moment. Okay. So the first one we're going to look at is substitution. Substituting is when you find what one variable is equal to, and you replace it in the other equation. So, for example, on the bottom equation, I'm going to move the 2y over to the other side, and I get that x is by itself. Once x is by itself, I can plug it in for x in the first equation. Notice that the x, I circled all the things that are equal to x in red, and we just replace that x right there with what it was equal to. And then it just becomes a simple matter of solving the equation because the only variable we have is y. So distribute that, we get this equation, and that makes 6y equal to 24 when you combine like terms. And if we divide by 6, you get that y equals 4. Now we solved one of the variables. We really need both variables though. So what you can do is plug it into any of these equations. Any of them work. I choose this one because I think it's the easiest. Just plug it into y right there and you get what x is equal to. So x equals 5 and y equals 4. Alright, another equation, another way to solve these equations is by elimination. That involves setting it up so that you have two variables that when you add them together, sometimes you'll see this as solving by addition or solving by elimination, when you add them together you get only one variable left over. So I'm going to draw this green line here, and I multiply the top by -3 just so that when I added the two equations together, the x's would add up to 0. Now I notice the y's do not add up to 0, which is a good thing here, and we get that equation in green when you add the two equations together. Okay. Then it's just a simple matter of solving for one variable and then plugging it back in and figuring out what the other variable is equal to. So there's just a little bit of algebra. We'll write this out right here, and you get that x equals 8, and y is 12. Now the third way to solve is by graphing it, and what I'm going to do is I'm going to allow you to use graphing to check your work on the quiz, but I really want you to show me your work for one of the first two to show that you know how to do those. So to show that it's an excellent check for work, I'm going to use the very first equation we used up there, the one that we used for substitution, and simply by plugging this into Desmos, which is what I want you to do now, pause this and hop on it over to Desmos. All you need to do is figure out where do they intersect. So I graph the two lines. There's the bottom one, there is the top equation, and where they intersect, 5, 4, that is the set of values that work for both lines. That's the solution to the system of equations. So you can see x equals 5 and y equals 4, which is exactly what we got up above. Alright, so you might be asking, okay, well, what if the lines are parallel? What if there is no intersection? Well, that's a good question. In that case, there are actually no solutions, and seeing parallel lines is a great indicator of that. You want to make sure they're exactly parallel, but here's what it looks like if you start messing with the algebra and trying to solve it, say, by elimination. So I'm going to first write down the bottom equation. We're going to multiply the top equation by -1.5. What that is going to do is going to allow us to eliminate the x variable. However, if you notice, it also eliminates the y variable when we add them together, and you get 0 equals -6, which is never true, so it is impossible to find an x and a y where those two equations are both true. If you ever get something like that when you're solving for using substitution or elimination, make sure that you check your work because you don't want it to just be a mistake, but yeah, it is possible that there are no solutions. Another possibility is, what if the lines are the same? What if they're right on top of each other? And you might go, well, that's silly. What, you would just be able to recognize that. Well, not necessarily. You see, these two equations here don't really look that much alike. In fact, at first glance, you might not guess that they're the same line. It's only after you graph it, and I'm going to hand draw the next one just so you see that it's they're right on top of each other, that you realize, oh, they really are the exact same line. So what does this look like with algebra? In that case, I'm going to use substitution here. You see the blue boxes. We're going to plug y in right there for that y, and we get that once you do the algebra and we distribute, we see the 15x minus 15x. Again, all the variables are going to disappear, but this time, instead of something that's always false, we get something that's always true. So it doesn't mean that any x and y work, but there are an infinite number of x's and y's that do work, and that is something that can happen as well. Alright, the last thing I'm going to do is I'm going to set up for you guys an application problem. If you take a moment to read this, you see that we're working with percent of a chemical. So you have a solution, and only 10% of is this sodium iodine mixture. Okay, so we've got 10% of this first flask here, or graduated cylinder, and then 60% of the second flask. We're going to add those together. We need to mix them in the right amounts. So we don't know the volume yet, but when we do, we will get a volume of 50 milliliters at 30%. So you can imagine if you mixed half and half, 10% and 60%, you'd probably get halfway between 10 and 60, which is not 30. So that is not the answer we're looking for. The trick to these application problems is figuring out what two equations you can get from the words. And there are two equations here. The first has to do with the volume. So if we label the volume x and y, since those are unknown, we know that the volumes need to add up to 50 milliliters. So x plus y equals 50. That's the easy equation. The little bit trickier equation is, how do we get that 30% sodium iodine solution? Well, you know that 10% times x, that's going to be how much sodium iodine there is in the first beaker, and then in the second one, y times 60%, also known as 0.6, is going to be how much sodium iodine there is in the second. And you know that the amount of sodium iodine in the third, in our final mixture, needs to be 50 milliliters times that 30%. So this is what gives you the other equation. The amount of sodium iodine that you start with, that you combine together, needs to add up to the final amount. So you see we have two equations. They look different, which is good. I believe they are different equations. And we also have two variables, so you can solve this. And I'm going to let you solve this. I want you to solve it before coming to class. Thanks, and I hope you learned something.